Okay, so now we're on page 31, and we're going to talk some more about the states of matter and how they can move back and forth between them. So as you have lower temperature, look, our y-axis here's temperature. At lower temperatures, you can have solids. At intermediate temperatures, you get liquids, and at higher temperatures, you get gases. In general, now, it can get a little funky if you also start talking about pressure, but we're not going to do that right now. So we're going to just keep to this general idea. When a solid changes to a liquid, we have a name for that. Like when ice changes to water, that's called melting. And we also have a name for when a liquid changes to a solid, that's called, yep, freezing. Easy enough. And we also have a name for when a liquid changes to a gas. We have quite a few names for it. Evaporation and boiling. Those are types of, in general, vaporization. That's the big one, the big word we're going to use, vaporization. Evaporation is a type of vaporization. Boiling is a type of vaporization. In general, those are just called vaporization. Evaporation only happens when it has to do with the air pressure and the pressure of the vapor pressure is what it's called, of the liquid in question. Evaporation doesn't happen at super high temperatures the way boiling does. I mean, when a puddle evaporates and you step in the puddle, it's not going to boil your foot, right? That's because evaporation works on a different mechanism than boiling does. But both are types of vaporization. And a gas changing back to a liquid, that's called condensation. Now, melting, freezing, vaporization, and condensation are all things we can find on this graph. It's called a heating curve, or in a way we could call it a phase diagram. I'm going to color code mine. So, melting, when a solid changes to a liquid, so that's when we're going in this direction. So this box is our melting box. What's different from melting? Well, freezing. That's when we're going the other direction. When a liquid changes into a solid, that's freezing. So keep in mind, we're starting with liquid here, solid here, liquid there, or liquid starting here, solid there. Depending on which direction you move, that's when you're going to have melting versus freezing. Vaporization would be liquid to gas, so we're going to use this arrow for it. That's vaporization. And our final one, condensation, when a gas changes backward into a liquid, so that's when we're going the other direction. Gas changing this way into a liquid, that's condensation. Now there are a couple other changes that do not get shown on this graph. Solid can change directly to a gas. That's something probably new to most of you. It's called sublimation. If you've ever seen dry ice, it's solid carbon dioxide. You stick it out at room temperature and it fumes. It kind of like smokes. That's because the solid carbon dioxide is changing directly to a gas. That's called sublimation. And you could go the other way and have a gas change directly into a solid. It doesn't become a liquid first, it goes from gas directly to solid. That's called deposition. And you don't see that happening often, but if you go somewhere really cold, like the North Pole or like Antarctica, sometimes you can take something like steaming outside and kind of throw it in the air, and the steam will turn directly into ice crystals or whatever if you're in a cold enough environment. So that would be deposition. And again, sublimation and deposition are not on this chart anywhere. Let's talk about a few more specific things here. When you have melting or freezing happening, you don't have just solid or just liquid, you're in the middle. So you have both solid and liquid with each other together when you have melting happening or freezing happening. And if you think about it, that should probably make sense. If you have ice melting, there is both solid water and liquid water in your container at the same time until all the ice is done melting. Then once all the ice is done melting, you're not melting anymore, you have just liquid. Or if you're freezing, you put some liquid water in the freezer. Once it starts freezing, you have some liquid and some solid together in that container until everything's done freezing. And once it's done freezing, then you only have solid. Same idea with vaporization and condensation. As long as there is vaporization happening, or as long as there is condensation happening, you have both liquid and gas together in that container. Let's talk about this word compressible. What does the word compress mean? What does it mean for something to be compressible? I'm going to write a little definition up here. Compressible, in one word, you could say it's squishable, or like squeezable. You can, the motion we always end up doing is like this. You can compress it, like compress it down. And you can't really do a lot of compressing with solids. If I take a solid and I try to compress it, like this highlighter, if I try and compress this solid, at most I'm just going to break it, but it'll stay solid. It is not compressible. It is the least compressible. And with a liquid, you try to squish a liquid, try to compress a liquid, it's just going to probably splash everywhere. But a gas, you can compress a gas. I happen to have a balloon here, and I can compress, let me zoom out a little so you can see this. I can compress the gas in this balloon. I can squish it, you know, I can squish it a little bit, squish it together. I can squish a balloon, I can squish a gas, because gases are compressible. You can get those particles close together. And the reason for that, if you think about it, your solids, if you try to squish them together, there's nowhere to go. The particles are already touching each other. Pretty much the same for liquids. But a gas, there's all that empty space. So you're not really compressing the atoms, you're compressing the empty space that's in between. And because of that, gases are very compressible. They are not only the most compressible, but they are highly compressible. They're very easy to squish. And that's because of all that empty space in between the particles. Let's make sure we remember what we said about shape and volume for solid, liquid, and gas. I'm looking for either the words definite or indefinite. Solids have their own shape and their own volume, so that means they have a definite shape and a definite volume. So that's something to remember about solids, that they have a definite shape and volume. Liquids do not have their own shape. They take the shape of their container, so that's an indefinite shape. But they do have their own volume still. However much space they take up, that's the same all the time. Liquids are indefinite shape and a definite volume. Gases, though, they don't have their own shape or their own volume. They have indefinite shape and they have indefinite volume. And when you're done writing that, let's look at page 32. The solid state of water is less dense than the liquid state of water. That's different than almost every other substance in the universe. Basically, pretty much everything else in the universe, the solid is more dense than the liquid. It's just water. That's the other way around. And this is why ice floats. Basically, if you look at solid water, the molecules, the HOHs, spread out to form this little hexagonal shape. Don't be afraid of the word hexagonal. What do I mean? I mean a hexagon, meaning 6 sides. And these hexagons leave all this empty space in between the molecules when you have solid water, ice, which means they spread out. So you have a certain amount of mass that is spread out over a bigger volume, and that's going to make your density smaller. Whereas in liquid water, the particles can get closer together because they're not stuck in this hexagon configuration. So that ends up making ice float. If the ice were more dense than liquid water, then ponds and lakes would not have this floating insulating layer of ice in the winter. The ice would sink, another layer of ice would freeze and then sink, another layer would freeze and then sink, and the organisms in the pond would be less likely to get to survive. They'd get smothered by all the ice as it sunk down on top of them. But liquid water is the most dense at 4 degrees Celsius while it's still a liquid, because its particles are as close together as they can get to each other at that point. Once it gets colder than 4 degrees, they start spreading out and forming this hexagon until they're totally frozen and stuck in that structure. So when the water begins to freeze, the molecules begin to separate from each other to form that hexagon, and that extra space in between gives you this lower density, which is what allows ice to float on water. So this is what's different about water than everything else, and part of why it's the stuff of life. Because as a solid, it's less dense. It spreads out in this hexagon. As a liquid, they actually get closer together. And then gases, they re-separate super far apart when it's steam. That's different from everything else. Everything else, pretty much in the literal entire universe, basically everything else, the solids are really close together, liquids still close together, gases super far out. Water's different. And when you're done writing, you can turn the page. Let's talk about changes in matter, but I'm going to do that in a different video.